I'm going to warn you ahead of time. The author geeks out for this section. I'm going to geek out in this section a little bit as well, because binary search trees are really powerful and really cool. So we mentioned in the last video that because of the exponential growth nature of trees that are balanced, complete, full, like all that sort of thing that we've kind of introduced but not formally introduced with the idea of balancedness, which is a weird word. Anyway, they grow exponentially. They're really big, which means that if they're arranged properly, we can search through them extremely quickly. So this video says, what does arranged properly mean? And the answer is a binary search tree. So a BST, a binary search tree, is just a binary tree with the following property. All right. We need every node, or actually, hold on, let me write it like this. Every node is greater than, in some sense, so I'm going to have quotation marks, all nodes in its left subtree and less than, in the same sense, all nodes in its right subtree. Okay, that's it. So it's just a way of sorting. So if we have numbers, right, every number is going to be bigger than the numbers on its left, smaller than the numbers, or smaller than or equal to all the numbers on the right. So this could also be alphabetically as well. If we're dealing with strings, we could organize this alphabetically. It really can be any ordering. Okay. Any ordering, but often it's numbers or alphabetical. All right, but it could be other things as well, but some kind of ordering here. And the reason why that's nice is if we're trying to find something, I'm spoiling this a little bit, getting ahead of myself. If we're trying to find something, we know how to find it because, well, is the thing we're looking for bigger or smaller? That tells us whether to go left or right. And we know we're making the right decision because it is organized. So let us look at an example. So we have two graphs here, two trees, two rooted trees, two binary trees, but only one binary search tree. And it's spoiled a little bit for you thanks to the graphic from the book. But the idea is in this left thing, which is a binary search tree, everything to the left in the left subtree of Mitch is earlier in the alphabet. Everything to the right subtree of Mitch is afterwards, after in the alphabet. Molly is close, but still alphabetically after Mitch. And then that holds true for every node. So if you look at Jessica, everything in the left subtree is before, everything in the right subtree is after. If you look at Randy, everything in the left subtree is before, everything in the right subtree is after. Now, that's why the right thing is not a binary search tree. Because look at Mitch. Everything in the left subtree should come before Mitch alphabetically. But Nancy is after him alphabetically. So Nancy's in the wrong spot. This is a binary search tree. This is not a binary search tree. It almost is. I think everything else checks out. Just not that one. So, why is it so powerful? I mentioned it before. Let's say we're looking for Molly. Well, if we look for Molly, we're going to start at Mitch. We'll say, okay, Molly, that's after Mitch, so let's go to the right. Randy. It's before Randy, so we have to go to the left. Owen. It's before Owen, we have to go to the left. Hey, look, we found Molly. We only had to do 1, 2, 3 steps, and this tree is height 3. That's always going to be the case. You need at most the height of the tree to get there, which is really nice, provided the tree is bushy enough. So perfect trees, really nice. Complete trees, really nice. But yeah, that's the idea here. And so here, of course, there weren't that many nodes to begin with. You probably could have found it faster by just looking with your eyes. But think about this. What if we had a tree with 2 billion nodes? Guarantee you would not be able to find Molly quickly if there were 2 million nodes in that tree, if you had to use your eyes. But if it's a binary search tree, you only have to look at 20 at most. That's the worst case scenario. 20 steps before you could find them. That's huge, right? I'm a math professor. I can say that 20 is way less than 2 billion. You can take my word on that. I got the degree to back it up. All right. So that is one super neat thing about binary search trees. And so if you've ever heard of big O notation, this is kind of where we get into that a little bit. Like, let's say that you're searching through an unordered list. So again, you can think of it as looking at 2 billion things and having to find something like I spy, where's Waldo, whatever. You have to look through things. It's unordered. That is going to be an, let's say, unordered list of n things. We say that's big O of n because the time it takes, or sorry, let's not say time, because time is really dependent on a lot of things, right? The steps required are proportional to n. So specifically in this case, if we're looking through 1,000 nodes to find one thing, on average, it's going to take 500 before we get there. It's going to take 500 steps, right? Because sometimes we'll get lucky and we'll find it at the start. Sometimes we'll get unlucky, we'll find it at the end, but on averages, it averages out to the middle. If it's an unordered list, it's going to be the order of n, big O of n. All right. It's not saying it's going to take 1,000 steps, but it's proportional. All right. If we doubled that, 2,000 nodes it would also double. That's the idea about big O of n. If it triples, the steps would triple. If the number of nodes quadruples, the steps quadruple. Big O of n means it's always just proportional to how many things you have in there. Now, conversely, right, if we search through a binary search tree, we only have to go at most the height of the tree. That's so powerful. What did I say the height of a tree was? Well, if it's perfect, the height of the tree is just log base 2 of the number of leaves. Okay? So, for example, and the book makes a stronger claim than I think is mathematically true, so I'm just going to include a less than sign, right? If we wanted to look, this is called big O of log base 2, of log of n, log base 2 of n, way better. And we're going to put this in perspective for you, right? So again, if we were looking through 1,000 nodes, on average, let's say actually worst case scenario, the worst case, if it's perfectly balanced, the worst case is log of 1,000. That's about 10. 1,024 is 10. This is very close to 10. That's much better than 1,000. If we double that, we don't double the number of steps. How many more steps if we double it? Remember what you know about logs. Oops, this is going to be 2,000. Just adds on out. That adds just one more. Oh, my head's in the wrong place. Log of 2,000 is just about 11. So it doesn't double the number of steps required. Really, really nice. Okay. And again, I'm getting really excited. We've already covered the point of the video, but just to really give a point about how logs work, right? If you look through 1,000 things, the log of that is about 10. To look through 500,000 things, the log of that is about 20. To look through 6 billion things, the log of that is around 33. So having something big O of log n, super nice. Okay, very, very nice. We can deal with very large things with very few steps. All right, and that is wonderful. And this is really an area that gets very mathematical, very, very quick, numerical analysis. I've taken a few classes in this in undergrad and grad school. A big study. This is for anyone who has had to take or will have to take, and that is everyone in this class. You will have had it, linear algebra, or you will take linear algebra. This is a big thing for numerical analysis in terms of like algorithm computation time, because matrix multiplication, and again, a lot of data is stored or can be stored quite simply as matrices. Matrix multiplication is very, very expensive. I think it's big O of n squared or n cubed. I don't remember off the top of my head, but it's very, very expensive, really, really badly. So a lot of things that we can do with matrices, a lot of simplification, a lot of decompositions for matrices really shaves down that that computation time by a ton. Thinking like LU factorizations, putting things in terms of triangle, lower triangular, upper triangular matrices. I think QR factorization of matrices. It's been a few years, but just off the top of my head, tons of cool things you can do with matrices, eigenvalues, eigenvectors. Again, I'm getting ahead of myself. This is not a linear algebra class, but just a lot of stuff that can be done to make algorithms work better, make operations go faster. Because at the end of the day, that is the thing for a lot of algorithms, right? Is like, sure, we can make an algorithm that does something, but if our data is so big, we need it to do it quickly. I don't want to spend 24 hours coming up with a weather forecast for tomorrow. In 24 hours, I'll look outside the window and know what the weather is, okay? So computation time, very, very important. I'm getting ahead of myself. It's very fascinating. I'm a little out of it today, but binary search trees are powerful because we can deal with very big trees and search them very quickly. That's the point. Have a good rest of your day. Bye-bye.